Kumar sir, Associate Professor, Department of Mechanical Engineering, NITW Warangal. What to Ms. Chimana Devi?
Dr. Anna, I am Ravi Kumar Saru, Associate Professor in Mechanical Engineering Department at National Institute of Technology, Warangal. He obtained his BTech degree in Mechanical Engineering from JNTU Kakinada in the year 2000. He completed Master of Engineering in Computer Integrated Manufacturing from PhD College of Technology, Coimbatore, in the year 2002. He obtained PhD in Mechanical Engineering from Usmania University, Hyderabad, in the year 2011 and postdoctoral research in 3D printing at Milwaukee School of Engineering, USA in the year 2012. He has supervised more than 30 MTech projects and produced 4 PhDs and guiding 4 more PhD theses. He also published more than 7 research papers in national and international conferences and also in journals. He has filed one international patent and 2 Indian patents in the area of 3D printing. He started MTech program in additive manufacturing in collaboration with Central Manufacturing Technology Institute, Bangalore, first time in India of its kind. Sir, I welcome you for this session, sir.
Yeah, thank you. Thank you, madam. So, very good afternoon, one and all. So, I think you might have just taken your lunch, or some people may be taking the lunch also. Once again, I welcome you for my second session. On this occasion, I'm going to talk on the file formats, standards, certification, and qualification of 3D printed parts. Basically, this presentation consists of 2 parts. One will be the file formats, that is basically STL file and the AMF file formats. So that is basically a neutral file format to start your 3D printing design. So it should bring in an STL file format. So I'm going to talk about the STL file formats and the limitations, advantages, and some challenges, and how it is getting addressed in newly proposed AMF file format by ASTM. So, and in continuation with that, I'm going to give you a kind of a state of art of the standards that the 3D printed parts currently is having, that is either from ASTM as well as ISO together. So I'm going to discuss the various standards and certifications and qualifications of these 3D printed parts. Primarily, that is either ASTM or ISO. So the current state of art of the standards, certifications, and the qualifications of the 3D printed parts. So these are the 2 aspects I'm going to discuss with you for the next 1 hour 15 minutes. So if you see in micro level topics, so it's going to be giving an introduction to 3D printing design and STL file format. STL file, STL stands for stereolithography, or otherwise standard tessellation language. You have a different abbreviations for STL, but basically STL is the stereolithography, and incidentally, stereolithography was the first technology invented by Charles Hull in 1988 commercially by 3D Systems USA. And incidentally, he himself, in one project, he has invented this STL file. Means almost 32 years old, this STL file format, but still it is going as a de facto standard. The reasons we will discuss, it has advantages, very good number of advantages, but at the same time, it has several problems and the challenges. On seeing the tremendous developments under this 3D printing area, then the ASTM and ISO, they have come out with say joining hands together to develop some standards and then say certifications and qualifications. So as part of their ASTM and ISO standards, the AMF was the file format suggested by the ASTM F42 committee. I'm going to discuss about this AMF file format, the syntax and semantics of this file format, and feature of these 3D printing data file formats. What could be the feature? And then second part of my presentation, which I'm going to discuss with you, is the ASTM and ISO standards of 3D printed parts for qualification and certification of the 3D printed parts. So this is what I have planned for this lecture. So as we understood, being a second day of this course, in order to start your 3D printing journey, your design is the primary requirement. That design should be in a digital design. So the digital design is going to be the start point of the 3D printing journey. So then, so for getting the design, actually, if you can even recollect the various steps of additive manufacturing or 3D printing process, obviously the starting point will be the modeling of your product that you are going to either craft or either it can be a simple coffee cup or whatever it is. So then we need to start with a 3D modeling of it by using some softwares and some workstations. Then you will be starting your 3D model. So once you're done that model, then you will be converting and transmitting that data to the machine. So then how do you get translated this data? Means I may be using CATIA, or I may be using AutoCAD, or I may be using Creo for that matter for as my modeling tool. But the native format of these modeling tools, your 3D printer cannot understand. So then we need to save that file, or we need to translate that file into an STL file. And then that should be send it to the, say, another software, the interfacing software, which we need to check for any errors. Then what are the chances of getting errors? That also we'll discuss. Then we need to check that STL file for any errors or any mistakes or any modifications sometimes we need to do. Then you do that checking, and once you checked it and everything is fine, and then you prepare a build setup file, and then that will be send it to the machine, right? And in the physically, say it's getting fabricated. So our focus will be in this area, and bit from here to here. How do you get transmitted this data, and how do you get check it, and how do you get prepared it? So that may be the the point of talk for during this session. But anyway, by using 3D printer, you could be able to print that physically by using this code which you have generated, and by using some post-processing methods. So then you will clean, and then you will further improve the properties by using some post-processing methods. So in order to remove the, or in order to increase the density of the parts, or the mechanical property or the tribological properties or microstructural properties, then sometimes you may use several post-processing methods. But anyway, then with this discussion, then we will move on to the next slide. So then we can understand how an additive manufacturing process, in particular to design, in particular to the data formats, which we are going to focus now. So either you start with the model capture, that is through scanning, 3D scanning technology. You can get it, scan your parts, and that is also one way of getting your digital data by using some softwares like Kinet Fusion or Autodesk ReCap or any other tools to reconstruct your physical objects to a digital objects by using the 3D model capture. That may be the one way of doing it. Or otherwise, you can adopt a CAD system. So right from the scratch, we can model it by using softwares like Blender or Fusion 360, Meshmaker, Rhinoceros, or any other software for that matter, which you are convenient or which you have that software at your organization. So then you can start your CAD design. That is another way of doing it. And either it is a CAD design or either it is captured from 3D scanning devices, then you come with an STL file here. And we need to, the STL file is a mesh file. So that mesh file is a triangular mesh file. So that it should be, say, sometimes we need to repair it. So why we need to repair that, we'll discuss very soon. So for doing a repair of this kind of STL files, you may have softwares like NetFab, Mesh Mixer, MeshLab, Magix, and several softwares available to do this kind of a mesh repairing job. And once it is free from all the errors and repairing that file, and then you have a slicer software which is specific to your machine or which is specific to your technology, the kind of 3D printer that you're going to use, that the appropriate software will be taken for generating the toolpaths or for generating the build setup. Then you may use softwares like Cura, Simplify 3D, Slicer for Fusion, or say it can be any proprietary. These are the open source softwares, or even it can be any proprietary software which is specific to that particular make of the machine. So then you can make use of these tools or the softwares. So then your 3D printing journey, the design, and further repairing, slicing, and finally generating the codes will be done. And then sometimes you may have some design libraries which is already existing, like Thingiverse, GrabCAD. So these are some of the online open source digital libraries which you can even download these models from their website or from their community, or you can be the part of their community and you can become the member. We can subscribe and you can start downloading these models, and even you can upload your models to that community. So then you have such kind of design library or a repository is normally called that as a repository. So you can even make use of repositories. So then in that case, we need not model, we need not scan. You can download from the libraries which is already existing from these kind of systems like Thingiverse or GrabCAD. And we have other, also I have some list I will display. It will come in the upcoming slides. So then with this, This is a typical design process and the tools available or the steps involved while generating your codes in your 3D printing process. So then when we are talking about an STL file, then what is an STL file is all about. So STL file is basically we need to interchange the data, like something like your laser printer or your say inkjet printer is there, how your either a document file or either a JPG file or a PDF file or a PPT, how it is getting recognized by your printer and how it is getting printed. Of course, in turn, your drivers may read this, may interpret this into in a PostScript form, and that PostScript form will be sent it to the printer codes, and it is getting printed. So the counterpart of this PostScript, in case of 3D printing, is going to be an STL file. So this STL file, so you can save your model in this STL file format by using any of your CAD modeling software. And once you save this model into an STL file, and then you can send it that STL file to the machine. And based on the code which you have generated in the previous slide also we were discussing. So based on that, it's getting printed. So it means basically your STL file as a PostScript like your, say, office printers or a desktop printers normally they do. So here is an STL file. So what is an STL file? So STL file, any CAD file, if you take for that matter, any 3D design file, so that consists of the geometry, means that is the coordinates or the dimensions of your model, and the color of the models, it's the rendered images, colors, and then textures. It consists of some textures in that model, and of course it consists of the material information also. But if you are coming from a CAD domain, you know better, like IGS is the one form, initial graphics exchange specifications, called IGS, and you have the step is another file format. So similar way, your STL file is the neutral format for 3D printing, unlike your IGS and step files. So STL file, unfortunately, it supports only geometry, but it doesn't support color, it doesn't support texture, it doesn't support material. So that is the problem. And more or less, STL file is a mesh. It is a triangular mesh. So this triangular mesh is, say, it's an approximation of your surface, basically. But you may have other file formats like .obj, that is object file. If you talk about object file, you don't need to convert it into triangles, or we need not tessellate them into facets. But here the free form curve will be represented in case of OBJ. But .obj cannot be understood by all the 3D printers, but whereas STL file is understood by all the printers. And your .obj file, it when supports color, it supports precision printing and precise printing and tessellation and freeform curves. And then if you have .mtl file, that is a material file, it consists of even material information, color information, texture information, everything. But whereas STL file doesn't support all these information about the color, material, texture, and so on. But still, why STL file is taking lead, or why it is a de facto standard, so that we will discuss. And keeping that into mind, so the ASTM, they have developed a standard called .amf file. So this .amf file stands for Additive Manufacturing Format. So Incidentally, Microsoft is also developed a new format called .3mf. So, but not all the 3D printers can recognize all these formats, but all the printers can understand .stl file, but some of the printers may take STL, you may even take AMF, 3MF, or OBJ or .mtl. Say, depending upon your printer capability, then you can use an appropriate file format. But STL file is a de facto standard. Every printer can read the STL file. But these are some of the recently or newly proposed formats which it will address the problems of STL. That we'll see very soon what are those problems and how it is getting addressed in case of AMF or 3MF file formats. And basically an STL file is a triangulated mesh, as I said. So if you have a cuboid, typically at the moment you convert as STL file, your entire model is represented into triangle mesh. And these triangles, say typically you have 6 faces in case of cuboid and 6 into 2. So on each face you may have 2 triangles and you may have 12 number of triangles if you take a typical cuboid. But if you take a sphere, the sphere is a more complex rather than non-linear or free-form surface than a cuboid. Cuboid is a flat surface here, but it is not a flat surface. It is a say circular and free-form surface here. So, which you may have more number of triangles in case of a sphere rather than in case of a cuboid. So then if you change to other geometry and you may have a different number of triangles which it consists of based on your geometry. But whatever may be the geometry, so your STL file, so how many number of triangles are there, and each and every triangle you have the coordinates. So I have the x coordinate, y coordinate, z coordinate. Why? Because basically it is a 3-dimensional data. I have the vertex v1, v2, v3. The corresponding x coordinate, y coordinate, z coordinate will be there in the form of a coordinate. And apart from my triangle, I have a normal. So that normal is a vector. So that vector coordinates also there in your STL file. So this is a typical ASCII file format. And if you go to binary format, binary, as we know that basically that is a machine understandable language. So either you save this in STL file as a binary or ASCII. If you save in ASCII, you could be able to read out your coordinates of the triangles. So it doesn't matter whether what kind of a form you are saved, but everything is represented in terms of triangles and their coordinates. And the STL file must say satisfy 2 rules. One is a right-hand rule, another one is a vertex to vertex rule. What is a right-hand rule is, so if your triangle belongs to an interior surface, so then you may have 2 chances. Either a particular triangle may belongs to an interior surface or an exterior surface. So if a particular triangle belongs to an interior surface, the notation will be the clockwise notation that it should follow in your data structure. That's 1, 2, 3 convention. And if it is the triangle belongs to an exterior surface, so it may be an anti-clockwise notation. That is 1, 2, 3 will be saved. So let's talk about the right-hand rule. And you have vertex to vertex rule. Vertex to vertex rule will say that you have 2 adjacent triangles, and the 2 adjacent triangles, it must have a common, say, side. So then it satisfies vertex to vertex rule. So typical any STL file, it must satisfy these two rules. And then what are the advantages of STL files? The advantages will be, so it will be easy conversion. What I mean by easy conversion is, so it is basically a planar, your file consists of a planar triangles. So a planar triangle, basically it is a simple of all polyhedra, right? So the polyhedra family will start with the triangle is the simplest of all the polyhedras, right? So then that is the reason it's very simple. Why it is triangle? Why can't it be other form? So the reason is, so it is simple of all polyhedras. So then it is very simple as it contains only the list of planar triangles. That's going to be the one advantage. And it have a wide range of inputs, means so all the CAD/CAM CAE packages will have this STL file as the tessellation algorithm. So it have this triangulation algorithms which are inbuilt and which is more popular or which is more widely used in all the CAD/CAM CAE packages. It's wide range of inputs are there, and it's very simple for slicing algorithm. So as we understood, you have to take your STL file, and next step it should be slicing in order to generate your layers. So that if it is a triangle, so it will be very simple mathematics involved, and computationally it is less expensive than any other shape. So the slicing algorithm will become simpler because it is a simple planar triangles. So that may be the another reason why the STL files are so popular. The advantages, once you can talk about this, it will become the slicing algorithms are more simpler. And even it can have the ability to split the models. Why we need to split the models? So my build volume may be limited, maybe say my build volume of the printer, say 250 by 250 by 250 mm, but my model is say 500 by 500 by 500 mm maximum size, then my machine could not accommodate that. So in that case, I can make it two halves, and then I can split that STL file into two halves, and then I can make separately and I can join it. So it is very simple to split the models whenever you require it. So that may be another advantage once you talk about STL files. And then what about the problems? So then you're talking about the advantages, then what could be the problems of this STL file? The problems are in several folds, so which it will be even say by the boundary representation, that is because of the approximation of your curve into a triangular facet or the triangular edge. So it is an approximation. And then you may have some intrinsic kind of say problems, like it may be in terms of file size or truncation error or incompleteness, inconsistency, inconsistent normals or incorrect normals. We'll discuss it one by one. And you may have, even because of your say CAD software, which there is an algorithm which it will convert into an STL file, or which is getting transforming into a test-related language. So then that may create some kind of gaps, or that may create some kind of internal faults, or some kind of degeneracy or some deviation, either in terms of geometry or in terms of topology. So then that may be, or sometimes incorrect intersections will also lead to then STL file problems. We'll discuss one by one these problems. And of course, as we already known that if you have some surface which is generated through a B-spline or a NURB surface or a Bezier surface. So that surface is, at the moment you save it as an STL file, so your surface is now as approximated with the triangle edges. So basically your surface now it is approximated in terms of triangular edges, triangular facets. So then where you are losing your data or where you have some error from the original geometry to the STL file representation, but you can't do anything. Why? Because this is approximation by the rule, by the syntax and semantics of this STL thing, which you are able to, you are losing some data. You are not transferring your data to your STL file or to your 3D printer from the CAD to the 3D printing format. You are losing some data. So basically you are approximating, you are not taking 100% data. And then you may have the intrinsic problems like the file size is too large. Why? Because you have a redundancy because of edge, but that may unnecessarily leading to the size, maybe bigger size. And your designer might have used your dimensions into a double precision real number, for example. But at the moment you save that data into an STL file, your double precision real number is getting truncated into a single precision real number, where again you got a truncated error here. So from the original designer, say geometry or the dimensions to the STL dimensions, you're truncating some values. So you have some truncation error. And it is an incomplete representation. Why? Because STL file doesn't support a topological information. So it consists of only the geometrical information. That is only the, in terms of say coordinates, it doesn't support the associativity or connectivity. Normally you call that as a topology, but it won't support the topology. Because of it is not supporting the topology, definitely it is an incomplete representation. It never become a complete representation. And inconsistency maybe that may be due to tolerances. Whenever you have some joining of the two STL files and you have that appending portion, which it may have some inconsistent tolerances, which you can come across. This may be another problem, which is intrinsic to your STL file format. And some inconsistent normals, like your normal should be every time it should be projecting outside perpendicular, and it should be projecting outside to the outer surface. But sometimes it may be projecting inside. So we need to flip that normals. That may be another problem, inconsistent normals. And some incorrect normals can also be, say, normally you have the triangle facet information or the triangle sides information. From the side coordinates, you can even reverse calculate your normals through vector calculus. Then, but it may mismatch your value that you have calculated and your tessellation or the conversion algorithm has given you the STL as an output. There is a deviation between these the calculated values and your software given values. So there is an incorrect normal is also there. And then you may have some data conversion algorithm, like say you have some triangle got missed. So you have one surface, you have another surface, and at the junction of these two surfaces, and by chance if one triangle got missed, and if one triangle got missed, say, then next step will be slicing. Say I have one slicing plane with 0.1 mm, means 100 microns if I am trying to slice this model. And if at all, if there is some triangle got missed, and it may not come to a closed boundary or a closed contour. So if it had been some triangle not missed here, and then you might have got the closed contour, but because of one gap or one triangle got missed, and it never become a closed contour. And if it never become a closed contour, and your laser or your extrusion nozzle so cannot have the clear cut path that it is going to deposit or that it's going to scan if it is a laser driven technology. So then you may have end up with a kind of a stray kind of a vector which is no endpoint. That's a basic problem once you have this kind of gaps or some missing of the triangles. And you may have some internal walls while designing. Say you may have one surface, another surface by designer misaligned or misproperly done this design. Then you may have this kind of internal walls problems may come into picture. And even some kind of deviation or a degeneracy. This may be due to even though you have the three vertices, but all three vertices are at the same location or the same coordinates, but that may not produce any surface, the kind of what you call. So it may not lead to any area. So once you don't have an area for, so it may become a kind of a deviation or error in terms of a topology degeneracy. But whereas it may have other way around. So though you have three vertices, but three vertices are not contributing to a triangle or the area. Why? Because all are collinear. So it doesn't represent any area of the triangle. So then this is called as a geometric degeneracy. So either a topology degeneracy or a geometric degeneracy may occur due to your data conversion or due to your transforming algorithm or a tessellation algorithm while converting your STL file. This may be the another problem which you can normally come across. And last one is because of incorrect intersection. Say none of the two triangles they never intersect. If at all, if it is intersecting, that is treated as an error. So means that we need to say place in a correct position. If at all, if it is misplaced, and if it is an extra triangle, then we need to discard it. So then, first of all, there won't be any intersection among the triangles. So then it may lead to an error. Then if you found some errors like this, and then which we need to rectify, which we need to correct those errors. Otherwise, if you are not correcting, if you are erroneously slicing it, the next step will be slicing. So your contours may not get a proper cross section. Means altogether you maybe end up with some build failure or build error. You may be anticipated at the end of the day. So then, as we know that in a computers, if you give a garbage in and you will get only the garbage out. So then you have to be careful while say handling this data. It should be free from all these errors. And then once you free from all these errors, then only you can say it is a valid model. So the valid model, you start with say 3D model, and then you slice it and generate the two-dimensional slices, and then finally you have a 1D slice, the scanning lines. And if this is the scenario for a valid or a watertight model, or the model which is free from all the errors. But if at all you have some error in your STL file, so then means in terms of some gap or missing triangle, and while slicing your slicing algorithm, say then it may get confused. It never form a closed say contour or closed boundary. So if it is not forming a closed boundary because of this, the triangle got missed, the connectivity got missed. So then it never form. Otherwise, if there is a triangle and it would have been a closed boundary, and then the needle or the laser would have been deposited or would have been filled this in a more meaningful way, because you have this error as an invalid, being an invalid model. So then your deposition may be abrupt, or it may have an infinite loop or a trace. It may create some stray vector, and then finally may lead to a build failure or may lead to a bad part production. So then, which we need to be careful while you are, say, operating with this kind of. And then what are the challenges that your STL file? So the STL file challenges will be duplicate information or the leaks, inconsistency, and it does not scale well when you have a high resolution data and lattice structures. And it does not support any color, and it does not support any material, it doesn't support any orientation. So then how do you get to address these challenges? Then that's what the ASTM is proposing, an AMF file format, so which it will be addressed all these problems and all these errors that we are talking about. So then how do you get it addressed by this AMF file format? So basically AMF file format, that is Additive Manufacturing File Format, is an XML script, and it is going to be the meta format or format of formats. So basically it is in a text-based script, basically, and it's an XML script. So it's a text-based file, and it is easy to read, easy to write, easy to parse, and easy to edit, and easy to extensible, and it can be highly compressed. The data will be highly compressed. So and the general concept behind this EMF file format is it is an volumetric data. It is not a mesh data, unlike your STL file. And even it will support the colors, it will support the texture, it will even support the multiple materials, or even it will support the grading of the material, and it will support the lattice structures, and it will support the mesostructures, and it is going to be say a consolidation of the objects, that is in terms of repeating instances, packing, and the orientation, everything it consists of, which otherwise STL file doesn't support all this information. And then how do you address this, the duplication of the vertex and the leakages of the triangles? So then you have this AMF will address such kind of duplication and the leakages because of the XML script nature. And it can be easily compressible. The compressibility of your AMF file versus STL. So you have an STL ASCII. STL ASCII is the biggest file. Why? Because it consists of all the coordinate information. And whereas binary file is a machine language, and which is consists of occupy less file size. And an original AMF file consists of in between, say, around 300 kilobytes versus say 200 kilobytes, and the say 780 kilobytes from AMF binary ASCII, vice versa. So, but whereas once you compress this data, so once you have zipped these files, so surprisingly, AMF should be in between these, say, binary and the ASCII. But surprisingly, so it is even, say, less than the size of an compressed binary. So then that's the advantage. The AMF is more compressible in nature than the STL file. That is another advantage, or how it is getting addressed by an AMF file format. Then you are saying that geometric inaccuracy may not be there in AMF file format versus STL file format. Why? Because STL, as we understood, it's a planar triangular patches, but whereas the planar patches are replaced with a curved triangles. So then whenever you have curvature, so previously STL file curvature is represented with a triangular edge, but here the same curvature will be retained because you are approximating with a curved triangle rather than a planar or a flat triangle. So then in that way you can address your geometric error through this curved triangles. And even if you have some say curved edges, and then there is an edge tangents also introduced here for whenever you have a flat edges, and whenever you have a curved surfaces, so your AMF file will automatically assign curved triangles. And if you have a flat surface, your AMF file will assign a planar triangles. So means basically it is adaptively, it is going to assign different kinds of triangles and tangents whenever it necessary. So in that way, the AMF is going to address the geometric inaccuracy that you come across STL files, but it is not there here. And even it can be recursively subdivision, like you can have one triangle, further it can be 4 power 1 or 4 power 2, and with the 4 power n, so we can recursively subdivide your, in order to improve the resolution of your file. You can even do this. And if you see the accuracy improvement or the error, so the error, a typical STL file with the same number of triangles, if you compare, so you have say STL file with the AMF with single fold, that is 4 power 1, and 4 square 4 power 6. If you come to 4 power 6 level where the error is almost negligible, so then that is where you can conclude that it's going to be a more say error free, or the accuracy is high in case of AMF file format. And even your materials can also be say assign different materials at the different regions. Why? Because your 3D printers can print in multiple materials. So why not your AMF file can represent say one region, one material, other region, other material. So that will be done with this AMF file formats, which it will be addressed by the multiple material representation of multiple materials. And not only multiple materials, you have some graded, functionally graded materials, or grading of the material across the length. So you have different compositions. So then you can specify that grading of the material in your AMF file format. And even it will address the microstructural, say, it will support the microstructural aspects. And then what is the current status of this AMF file format? The ASTM F2915 is the standard for AMF, and the first revision 1.1, it was come out in 2012, and this is under adoption, but still the adoption is not that much great by all these software people, but still now it may be going a different version. The current version they are developing. So then we'll discuss more elaborately in the upcoming slides about these standards. So then you may have, they may have the future plans for AMF while it is getting incorporated while developing the next version of this AMF file format. So they have a plans to incorporate the tolerance information, like you have the step file versus IGS. The step file consists of the tolerance information rather than your IGS file doesn't support. But your AMF file, it is they are planning to even include the manufacturing tolerances also that will be included in your AMF file format. And they are planning to have the surface or a depth kind of a textures to be incorporated, and data inscription and copyrights and external references and subassemblies and process control is also another aspect which it can be included in your AMF file format. And in non-volumetric support structures also, it is going to supported by your AMF file format. And even it can be a non-mesh geometry also, like it is going to be an voxel or a feature-based representation. Also, they are trying to incorporate these features in the new upcoming version of the AMF file format. So with this, some of the future plans, then we have thoroughly discussed the STL file format and AMF file format, the various problems, limitations, challenges of STL file thoroughly discussed, and how it is getting addressed in AMF, that also we have say covered. And then what about the code, and what about the contour data, or whatever the something like G code, M code in case of a CNC system. But whereas here you don't have a common file format, so different vendors may be using their own proprietary say formats for this contour data or this cross-sectional data or the layered data. So like you have SLC, SLI, CLI, RPI, LEAP, like that. But unfortunately, there won't be any common format for this kind of contour data. And in contrast with additive manufacturing, you may have in a conventional CAD systems, like as I already said, like you may have IGS step, and in case of medical domain, you have a CT, and in case of printing, you have HPGL. So the file translators that typically you can come across. In other than AM, you can have a CAD or the medical field normally you can come across. So with this, I have completed my first part of my presentation, and let us talk about the next part, that is standards, ASTM or ISO standards. So then, first of all, what is a standard is all about? Say the standards, that is something to be measured or to have some norm or to have some model in comparison for your evaluation. Means you have produced some part. So in the last session also, so participants were asking the questions like, how do you get the repeatability? But how do you ensure that whether you have made a good part or a bad part? Until unless you doesn't have a standard, until unless you doesn't have a benchmark, or until unless you doesn't have some reference, so which is not scientific way of taking a decision whether it is as for the standard or as for the norm. Normally you say that, right? So that is exactly what a standard. So if you see the ASME definition of the standard, so it is a standard can be defined as a set of technical definitions and guidelines, that is how to kind of instructions for the designers or the manufacturers and the users even. So you can buy a product, then how can you ensure that it is as for the standard, as for your expectation, and that expectation is as for the standard available. So especially if you are exporting your products to some other country, so then it should be, then only the people will buy and people will trust you, right? Otherwise, so until unless saying that some ISO standards or ISO certified companies, right? So then only people have some confidence on you. So then people will buy your product. So that's about the ASM definition. And even ISO has defined the standards as the standards gives a world-class specifications for products, services, and systems to ensure quality, safety, and efficiency. So that is the thing where you can be say. So it requirements, specifications, guidelines, or characteristics. So then the standards are very much needed for the 3D printing. Why? Because relatively new technology. Until unless you doesn't have a standard, you cannot justify whether you made correct part or bad part, or how do you ensure that it's getting correct or not, right? Say until unless you doesn't have a standard. So then why we need a standard? So the standards gives a business and the consumers confidence, right? So that the goods or the services that are say they are developing or using are safe or reliable and will do the job they are intended for. So basically it will give you a kind of confidence, or it will give you a kind of say business opportunity if you're a manufacturer. So then how the customer will trust you, right? So then once you have these kind of standards and certification saying that it's ISO certified, right? So then people will have a confidence that yes, you can buy this ISO certified product or ISO certified say brand, right? And the standards which helps make laws and regulations so that can consist, right? Say you can go to court, you can file a case legally, you can proceed saying that this is not as for the standard. Until unless you doesn't have a standard, so you cannot claim legally, right? So then it will help you to go within a aspects also. It will, even the standards will, the products that say comply, whether that complies as for the standards, so which it will give some kind of competitive edge for your products, especially if you are in an international market. Why? Because people will look for what kind of certification he or she is having, right? Who got qualified, or who has given the certification for your products. If you are an international player, then this is very much needed. And to ensure that either it is the materials or the products or the processes, or even it can be a services. So those are fit for their purpose. Then that's what we need as standards. So that is very much needed for. Nevertheless, the 3D printing or additive manufacturing industry is looking for. So whenever you want to industrialize, say if you are using for a domestic purposes, so then it doesn't require your standards, or this doesn't get certified, or that is purely for your internal consumption or only for the domestic based. But once you are elevating this technology to the industrialization, so AM or 3D printing is getting, then it can be further getting industrialized or further matured. So definitely, so your AM industrialization may happen only. You must have the standards, and based on that standards, so somebody has to qualify your products. So, and finally somebody has to give some certification, so some ISO certification or some ASTM certifications or DIN standards. DIN certification are Indian standards or some kind of thing which somebody has to say test it for the standards which is existing in the universe across the globe, or it can be a local standards. So then get it qualified and finally get it certified. So then the standards are the very much needed, or the key for AM industrialization. The standards, it will ensure your process control. So, and then it will ensure the product quality assurance, and it will define the levels of criticality, right? So, and it will reduce the risks of your failure, or risks of somebody was asking, I am not getting my SLM parts are not more reliable, or I am not getting a consistent builds. One build, another build, or one location of deposition is varying. I am not getting a consistent accuracy, of course. So then once you have these standards, then you can have the reference as these standards, or you can follow those ASTM or ISO standards, in ensuring that your process control or your risk of failures, or even it will reduce the cost also, right? Ultimately, so that is our aim. And then it will sometimes it will now say standards will ensure, which will facilitate a larger adoption. Like say, yeah, that is like confidence levels are the Barossa, right? Say yes, it got certified, or it got qualified, or it is as for the standards, right? And then it will have more adoption, and which will have even impart some trust and some confidence among the customers about your product. And then certification and assurance also will lead to your standards, can ensure that. So then AM industrialization, so it relies on, so it should start with standards, so that is come out with a more number of standards that should come out. I will tell you the state of art of standards that are available across the globe. At that, I'm going to give very short time. I'm going to say give you the statistics of it. So, say any time against to the mechanical tests or thermal tests, which will follow some ASTM so and so number. So then you can say that I have done designing, or I have done followed while building, or I have done the post processing. So in that way, which it can be dimensional metrology is more improved if you are having standards that you should follow while fabricating these kind of things in additive manufacturing process, and some guidelines and the best practices and data formats that just now we have discussed. STL file having a lot of errors. So your data formats and retentions, and your raw material is consistent as for your standards, the powder particle size, or the flowability, or the viscosity, or things like that, right? Say which it can be as for that the raw material. or your feedstocks, or as for that, and the types of AM process and the calibrations should have, and the machinery safety. Also, once you have the standards, and post-processing monitoring can be done, and in-process monitoring, all these we could able to achieve, say, best quality of your additively manufactured parts once you have a kind of, say, standards. So then coming to the AM and the ASTM. So as we know that ASTM stands for American Society for Testing and Materials. So ASTM have several starts from A series, maybe steel, concrete, like that. But coming to the additive manufacturing, you have F42 as allocated for additive manufacturing standards. So ASTM F42 stands for additive manufacturing standards. And they have, even as I have been talking about, they have classified your AM systems into 7 categories. So that is as for the agreement of ISO and ASTM. So actually, these are the two independent bodies. As we know that ASTM is an American society, and the American, then this is an international standard. But Americans, or even ASTM has formed well before the ISO has formed. So then ASTM has a long history, or it has been started long back. And then even whenever they have an agreement between the international standard and American standards, so you can see then ISO bar ASTM, this is a combined, say, standards that has been developed from international as well as American standards. That is, say, 52900. 15 stands for 2015. It got, say approved, or it got into the, say, published, rather than 2015 it got published. So that is all 7 categories of AM. So why? Because people may giving a different classifications. Like Chua has given a liquid, powder, and solid, but whereas Brent Stucker or other people might have given a different aspects of these classifications. But ASTM has standardized in 2015 into 7 categories. That is one general principles and terminology. So as I said, like, ASTM committee has formed in 2009. So, but incidentally, ISO has formed, whenever you can find the ISO standards, that is 261 refers to additive manufacturing for ISO standards. So it has formed in 2011. So 2009 ASTM 42 committee for looking for the additive manufacturing standards has formed. So one can understand this technology started in 1984-85, but whereas ASTM standards are started in 2009, and further ISO standards are 2011. And say you may have a general, say, top level AM standards and category wise AM standards and specialized AM standards, means application specific or process specific or material specific. Say then you can categorize into 3 subgroups. And again, in the general AM standards, you can even start with the terminology. Just now we are talking about, they have given some standards for terminology, that is ASTM F2792, say 12A, and from ISO standards, that is ISO 17291 2961, and the combined ISO and ASTM, you have 5292113. That is the general terminology aspects. And whereas the process specific and material specific, you have ISO standards 172962, and qualification and certification methods. So somebody was asking in the previous session, then how do you ensure that your qualification and certification could be done? So then you have a separate things for qualification and certification methods, and requirements for the purchase of AM parts. Say you want to get some service from service bureau, then if you have some standards, and then you can issue some legal notice to the service bureau saying that it is not as for the standards, right? Then you may have some requirements for the purchase of the AM parts, that is also is there. And non-destructive evaluation methods, like you have some, say, tensile test, dog bones, right? Say even for the AM, you have some non-destructive evaluation methods, so which it is getting. Of course, test methods, again, you may have ISO test methods and test artifacts and general test methods, performance test methods, and design and data formats. Just now we are talking about your 52915. So that is an additive manufacturing EMF file format. So that is developed in 2013. So then ISO 17296 and then data structures and matrix for AM models. And then coming to the category of AM standards like a raw material. So the raw material, so you may, if it is a metal powder, then you have the standards that is for either it is a powder bed system or a DED system, you have a different, characterization of the powders. So then metal powders and the polymer powders, you may have a different characterization. So for photopolymer resin, say it should have more, so the less viscous, say it must have the more flowability if it is a powder particle, right? And if it is ceramic, so then it may have some other characteristic. And if it is a composite, it may have some other, right? Say which the raw material should have, say specific category, and it should even specify the specific standards like say what could be the viscosity and what could be the flowability, chemical composition, right? So those kind of things can be addressed here as a material specific specifications. And similarly for the process and the equipment, so whether that is a powder bed system, and again in the powder bed system there's a titanium 64 or Inconel 625, or it may be other steel or aluminum, or it can be other material. So then you have that material, the powder bed systems and material extrusion, like you may have ABS, PLA, right? And you may have PEEK or Altem. So you may have plenty of things that, and then direct energy deposition. So you may have different materials and so on and so forth. And then in specific to that, the standards like process specific performance test methods, or process specific test artifacts, or system component test methods. So, and then coming to the finished parts, so like the standard protocols for round robin testing, like mechanical tests, like say, so you have tensile test, and you have porosity test, and you have tribological or fractural toughness, the fracture toughness that we need very much needed for your aerospace and other applications. So then you have a specific, and these are specific to metals and specific to polymers and specific to other materials. Unfortunately, you cannot standardize these materials, and particular to it will behave differently if you are using a powder bed system, you have a different ball game, and if you are using say injection, say you have jetting technology, altogether you have a different ball game. So then we need to have a part specific things here, and then the finished parts and application specific, say some GE, right? You talk about aerospace, GE, like people like GE or Boeing, Airbus. So they may have a specific application requirements, and they may have specific standards that are collaboratively developing with ASTM and ISO. And for medical implants or medical devices, so or even automobile, they may have application specific standards they are developing. So this is some of the structure of an AM standards that is so typically, so this is a typical say categories, and the chance of getting the ASTM standards from and if you see as on date, I'm talking about as on date, you have say ASTM F42 subcommittees they have, and then for the test methods, you have 3 published ASTM standards, and 4 is under development. And for design, you have 2 existing and 5 under development. And materials and processes, 9 existing and 20 under development. And environmental health safety, none of the standards available under this, but they have reserved this number. Maybe in future it can be. And execution, none of the ASTM standard available. And strategic planning, nil. And then terminology, 1 is existing. And tag to ISO, nil. So typically you may have very few ASTM standards. Maybe if you subdivide into test methods and the other stuff. So then coming to the test methods, so these are the methods, test methods. So the standard that is F297113. So that is for reporting the data for test specimens, which is prepared for the additive manufacturing. This is exclusively for testing, preparing the test samples or specimens. For this, we need to refer. And we need to mechanical properties for metal materials. You may have a different, say, if it is a metal, that to metal materials for evaluation, and then you may refer F312214 ASTM standard. And then coming to the ISO and ASTM combined effort, so that is 529213. So this is for standard terminology for additive manufacturing and the coordinate system and testing methods. This is the combined ISO and ASTM. Wherever they have the understanding between international and ASTM, that is combinedly they have published. And design the AMF. Just now we are talking about our AMF file format, which will come under, that is ISO ASTM 5291516. That is AMF file format. Just now we have discussed, that is 1.2 version. 1.2 version. And then you have a design for additive manufacturing, DFAM. So DFAM standard guidelines, you can refer ISO ASTM 5291017. And coming to the terminology, this we need to refer for terminology, that is F4219, and ISO ASTM number is this one. And similarly for the materials and processes, especially for the powder bed system with processing of titanium 64 aluminum vanadium, so you have this standard should be referred. And if you have ELI composition, that is extra low, say ELI kind of thing for powder bed for the same aluminum, titanium 64 for ELI grade, you may have this standard should be followed. And for characterization of your metal powders for additive manufacturing, you should refer this standard F304914. And for materials and processes, the standard specification for AM nickel-based LI, that is Inconel 718, we need to refer this. That is for powder bed system. And DED system, we need to have a different standards. For powder bed system, looking for Inconel, that is 718, and we need to refer this F305514A. And then you have a slightly different nickel grading, the Inconel different 625, and you have to refer these standards. And this is about the nickel-based LI. And if you're looking for a polymer material for powder bed system, then we need to refer either 3019 or 3091 M14. That is for the plastic powder bed systems. And even for stainless steel, if you are looking at with a powder bed, and we need to refer 318416. And the DED system, that is direct energy deposition of metals, we need to refer F318714. And then you have ISO ASTM 5290116, that is for standard guide for additive manufacturing, general principles, and purchase of AM parts. This is quite important if you are getting some service or some service bureau, you want to get it your parts, and then it should ask for these standards or not. You can very well check it. Otherwise, you can proceed legally on the service bureau. And then you may have terminology related, and you may have general principle related numbers, and then main characteristics and corresponding test methods. You may have a different materials and testing for ASTM existing standards. And similarly, from the ISO side, indigenously, they have developed. Whenever they don't have the, say, agreement, not agreeing with the ASTM, then they have come out with the ISO. Whenever you find ISO, that is indigenously developed by ISO. But this is again a combined ISO ASTM standard for general principles and the same thing. But whenever they doesn't have an agreement, then you can find some ISO kind of standards. You can refer if you are looking whether you want to follow an ISO or ASTM. So then that is up to you. Like you have these published standards which you can even. So then they have a joint plan for additive manufacturing standards developed for the thing. You can go through it, but finally then you may have the ASTM and the EAM. They have come out with the Center of Excellences in the R&D themes, like in terms of design data and the modeling and feedstock material testing and EAM process, post-processing, EAM testing and qualification of the parts, and which we have summarized. We can even summarize those, say F42 means basically is in ASTM standards for test methods, or for design, for materials and process, for environmental health and safety and applications and future. They have allotted this 42XX means it's a future development. So for the NDT and other tests, even they have a mechanism to have defined based on the Center of Excellence, the R&D teams. And since somebody is looking for some kind of PhD problem, and where these are some of the challenges, still the AS team is looking for some kind of developing the standards, right? So, and then this R&D, actually they have come out with some R&D projects, and 2018-19 they have sanctioned 5 research projects. So the first research project based on the metal additive manufacturing testing, and second one is on post-processing, and third one is on feedstock evaluation, and the fourth one is a powder bed process qualification, phase 1. And then why? Because next year also they have given us a phase 2, and polymer EAM testing, the specimen design, and this is addressing the 7 standards gaps, and then which may be impacting around 20 standards. These 5 research projects or R&D projects that they have given to NASA or MTC or EWI or NIR or some universities also collaboratively they are doing this. And now recently also they have advertised for the proposals. If somebody is interested, you can even propose, you can submit your proposals based on these themes. And even you can have the present 2020, 19 to 20, they have 9 research projects in powder bed process qualification, phase 2, the phase 1 that is given to the NASA. And then they have a project that is design guidelines for EAM process, design for post-processing methods, and polymer EAM design, say value testing and rapid quality inspection specimens, dynamic testing of polymers of additive manufacturing, and in-process monitoring. This is upcoming, very interesting stuff. The project is in-process monitoring systems, and EAM powder spreadability. This is another theme of project. And data, say you have the data. Nowadays, you have the data security or the cyber security or the blockchain technologies, even that can be. So it may be 20 gaps it may address in various standards, and then it may be directly impacting around 43 standards. So yeah, so then in order to summarize, say then ISO ASTM for general guidelines, you have 1517, this ASTM 52900, and design for additive manufacturing, you have 3, and feedstock related, you have 1 here, and EAM process, you have material testing and post-processing, and EAM environmental and the safety aspects. It's yet to publish, so it is under development. And equipment safety, you have ISO ASTM 52915, so 2016. And let me conclude what I have done regarding the standards, like say, so combinedly with the ISO and ASTM, approximately there are 25 ASTM standards or ISO standards combinedly. So 25 got published and 50 under development. Currently, there are 50 under development and 25 under, this is already published, 25. So either a general AIM standards, that is AIM terminology, test methods or safety, that is under general AIM standards, and application specific like automobile, medical, and so on, and feedstock material standards, metal powders, polymer filaments, and process and equipment related standards. You have powder bed fusion, material extrusion, etc. And finished AM parts, that is post-processing methods and non-destructive evaluation. And then this is the, as on date, the globally, the ISO and ASTM standards for additive manufactured or 3D printed parts. So let me summarize and let me conclude my talk here. So we have started this talk with the importance of 3D printing design and STL file formats, advantages of STL file formats and problems and challenges, and how it is getting addressed in AMF file format, and future of AMF, and the future formats of data file formats, and ASTM and ISO standards for additive manufactured or 3D printed parts, and qualification and certification, and the state of as on date, how many are, it's at about 25 plus has already published and 50 under development for additive manufacture standards, together ISO and ASTM. So yeah, anyway, these are some of the facilities which we have at NIT Warangal. So we have a metal powder bed system, DMP Flex, and we have Status Dimension, FDM machine, Mojo machine, Ultimaker 2 Plus desktop, polymer printer, any scan, sun scan for scanning, and muffle furnace and short pinning for post processing. And we have 3D printing softwares like Mimix, Magix, 3matic, Catalyst, and 3D Expert. And we have YouTube channel also. If you're interested, I will paste it, the link in the chat box. You can follow in a YouTube channel also. Yeah, I think I have done from my side. So if you're having some specific questions, and then I'm happy to answer those.
That was again wonderful and resourceful session, sir. Your all
Thank you.
sessions were always resourceful, and definitely we will going to have research projects and theses of PhDs. They will going to have more research on these areas.
Yeah, thank you.
Now I would like to ask the student participants, professors to ask the questions if they have any queries. Any questions?
No sound. No sound.
Hello.
Hello?
Yes, yes, you are
Any
audible now.
questions? Yes, yes, you can ask a question directly. You're live, sir. You can ask question. So you said about the STL file format. So ASM file format is better. You said that depend on the geometry, we can have ASTM file. We can print any object with respect to the complexity also in AMF format. Additive
Right.
Manufacturing format.
Right.
So in that, if a triangular file is there, so if I want to change the shape of this particular layer, so only for particular layer, how can I change the triangular shapes on particular
No,
layer?
no. Actually, there is a slight understood, a misunderstanding. Why? Because actually the STL file is well before the slicing. The slicing, the layers will come after, say, slicing will be done on the STL file.
Okay.
Okay. Say the slicing will be done on the STL file. Once you slice the STL file, so those cross-sectional, the intersection point of your plane and the triangle,
Okay.
you join, then you will get your contour. So yeah, the STL file is well before the slicing thing, and once it sliced, and now you will get only the contour, the cross section. Now, what is your question? I am not getting like.
Suppose some of the there are some of the gaps you
Ah,
explain void, so some kind of
mm,
vacancy or some kind of
right,
lagging. So in that
correct.
case, what procedure, what step we have to take care in order to reduce or remove that particular error?
Hmm. Yeah, actually, we need to. The typical practice is now you have some softwares like Magix,
Magics, yeah,
um, you have say a mesh.
you are not audible.
Then the software will automatically identify that and it will be getting corrected.
Okay.
But if it is an AMF, and it may not be there, but once the AMF will come into full-fledged adoption in all the softwares, then there won't be the requirement for this kind of repairing algorithms or repairing softwares. But as of now, the STL file, and then because of these errors, so then you may be using softwares like Magix or Mesh Mixer to getting repairs. But if it comes to an AMF file format, so these errors may not be there. Basically, yeah, it's going to be the foolproof kind of format. Yeah. Hello.
Yes, sir. I've
Yeah.
finished your answer, sir.
Yes.
So is there any questions?
Hello, good afternoon, sir.
Good
Yes, good
afternoon.
afternoon.
Yeah, this is Naresh again. Actually, I have a small doubt, sir. How do we qualify the STL file? So, like, since STL file is yes, sir. Since STL file is a mesh file,
Right.
so if you want to qualify the mesh properties, like since like we have 7 of mesh quality properties. So
Mm,
it kind of maybe aspect ratio, skewness,
mm,
flatness, or Jacobian matrix, whatever it may be. Whether these properties will affect the 3D print or not.
mm.
Hello.
Yeah, yeah. Hello.
Yes,
Am
sorry,
I?
sir.
Yeah.
Yes, sir. Yes, sir.
Yeah. How do you get qualified your mesh file? So that's going to be the yeah. That's what like ASTM. They are not. They want to discard STL basically. They doesn't. They doesn't want to say continue with the mesh file like STL. They want to discard. That's what their intention is to say replace the STL with the AMF, but unfortunately it is not happening. But definitely it is getting affected by these aspects of your mesh files. But the AMF is not a mesh file basically; it's a volumetric
Uh,
representation. So yeah, that will address all these issues definitely. Once the AMF into in a full-fledged way and all the 3D printing and CAD/CAM CAE vendors, it should come from their side, right? Like say you have a 3D printing community and 3D printing this thing. So then, but the start point should be from a CAD perspective or a CAD/CAM packages. So then the package the developing vendors who are developing these CAD/CAM packages. So first they should adopt number one, and then according the slicing algorithm should be revamped or should be say retune as per the AMF files. Why? Because the existing file, but it should be rewritten in terms of the AMF in tune with AMF. But yeah, it should come on the both the sides. Like it should be accepted by the adoption by the CAD/CAM CAE vendors as well as 3D printing the developers, the slicing algorithms and the toolpath algorithms should be rewritten based on this EMF. Maybe if it happens, then it could be the betterment of these. It will address several issues, the errors, or I'm talking about at least the design aspects, but hardware aspects and other issues, then that should be a different thing. But especially for the representation or the design data side, it can be, some extent, it can be addressed by this kind of standards once it will come in a full-fledged way, like AMF should be adopted by all the people, yeah, in this space. That,
Yes, sir. So what I have done is like when I got this doubt, I have performed mesh matrix analysis in one of the tool hypermesh. I have performed like I have checked the mesh quality, sir. So with that using the tool, I have done some mesh quality improvements and I have done print. So I'm getting not much, but getting some better results on a curvature somewhere. So I'm getting the better results. So on that prospect, I just asked about this. Thank you, sir.
yeah. Actually, there is no foolproof here, like saying addressing some standards of ASTM or ISO to check your healthiness or the mesh accuracy or in that aspect. But their idea is to even discard the mesh files to have volumetric data. But it may be bit laborious or it may be bit complex. It may be bit computationally expensive for slicing algorithms, definitely, than with STL.
Yeah, sure.
But
Yeah,
somehow it
that will
should
be
be.
because when it is rendering the complete value, so during the slicing, generating the each and every like for each and every cell they have to generate on like it has to read each and every cell, so it will be very
Right.
difficult in
Yes.
developing, sir. Yeah,
Mm-hmm. Yeah, those
thank
may
you,
be
sir.
the reasons like why it may not be happening in a quicker way, adapting, and then yeah, maybe that these are the reasons why it is not happening in a quick manner or adoption may not be happening as we expected. Yeah.
Even all these NetFab, Meshmixer, few of like STL repair tool also, they are not capable enough to solve each and every problem in
Right.
STL file. I have seen few problems which
Correct.
I couldn't solve in the Meshmixer or NetFab, which are free source softwares. So I couldn't
Yes.
able to solve in that. So I have used another tools,
Mm.
design softwares. I have used design softwares to solve the STL problems most
Mm.
cases. So
Mm.
we're kind of self-intersecting geometry is one of the major man-fold geometry, like
Okay.
where we can't even solve these kind of problems. So self-intersecting, actually,
Mm.
while I'm modeling, sir, there is one yes, it's a surface model, sir. So while I'm designing, I didn't observe it. So there is a self-intersected geometry was created. So when I'm doing the analysis further, so I'm getting very bad results on my final product. So
Okay.
these kind of a self-intersecting geometry, these mesh mixture or netfab or these kind of softwares are unable to solve and unable to identify also sometimes. So for
Mm.
that, again, we are working with other designing tools. So there we are
Mm.
getting so much of problem with headache and when some kinds of normals also, sir. When the surface normals also when they got flipped out, so they
Yes.
will be hidden. So these kind of a problems are facing very difficult with the mesh mixture and this kind of a stuff.
Yeah. Yeah. Yeah, Naresh, you are a JRF or you are a scientist there?
At present, as a JRF, sir.
Okay. Yeah.
And
Okay.
actually, few of your college students also they came from project, so
Mm-hmm.
they have done projects and done mine own.
Okay.
I have done
Great.
with them, sir. Yes,
Okay.
sir.
Okay.
Actually, I'm
Ah.
supposed to. Yeah, sir. Can I leave your contact details, sir, please?
Yes. Yes.
Yes, sir. Thank you so
Yep.
much.
Yes. Yeah.
Yes, sir.
Okay, Naresh. Okay, Naresh.
Yes, sir. Thank you.
Right. Right. Bye. Yeah.
Sir,
Yeah.
and
Hello.
another question. In
Mm-hmm.
STL file, what is the relation between image sharpness, precision, and density? There is number of triangles per unit area.
Mm-hmm.
So what will be the relation? She's asking Jenny. what is the relation between the image sharpness, precision, and density? So how to we control these process parameters in terms of the number
Yeah.
of triangles per unit area?
Yeah, no, actually, that's what actually you don't have much control on that. Like say, you basically you may manipulate with card height actually, card height and the angle control. There are two parameters that you can control with say chord height is basically the tolerance between your original say profile to the tessellated or approximated triangle. So that tolerance or that gap, you could even able to control the what you call the number of triangles which you can. Obviously, once you reduce this tolerance value, you can get more finer mesh, and even the other parameter which you can operate will be the angle control. So this angle control also will allow you to bridge the gap or to some extent reduce the error from your original curvature to the tessellated curvature. So you can you can try these two. Again, it will vary from one software to other software. Yeah, so but normally you can control with this tolerance, or otherwise called as chord height. Normally some software they may call chord height, other software they may call that as the tolerance. So you can try with that, or even you can try with angle control. So the deviation from that also, can it be 0 to 1 will be the typical value, and then you can vary between these range, and then you could be able to vary your resolution of the mesh. Yes, it could be.
Sir, I would like to continue the question of Ashok Kumar and Ms. Deni that if
Sure,
we are
sure.
not getting the accuracy of what we are printing, that means our nozzles and our equipment should also match with the output which we required. So I want you to say a few sentences about this
Sure,
to
sure.
clarify my doubt. So, what type of nozzles which will going to be used for better accuracy and surface finishing, so that we can have the better accuracy. So we should not use the same normal nozzle for as we are printing for 1 mm or 5 mm accuracy for that. So I request
No,
you
no, the
to
nozzle for which, no, nozzle for which FDM you're talking about, FDM
FDM,
or,
sir,
okay,
FDM.
okay, okay.
FDM. So what are the various better for getting better results as we are expecting? We are giving one input and we are changing the shape of the triangles, and we are doing mesh using mix matching software also. But at the end output, if we are using the same earlier traditional nozzles, so we're going to get the same output results. So
No.
so is equipment also required for this DM process to have what we are expecting, what we are giving inputs, what we are doing meshing, and the same results will going to be reflect on the bed. So the equipment like nozzles and temperature, other process parameters will going to play a good role. So that I want you to say a few sentences on this.
Okay. Okay. Yeah. So you are asking me the question, like I am not getting you. Yeah, like definitely. Yeah, this is one aspect of the thing, and then how it is getting coordinated, yeah, with the hardware, and then how it is getting.
Hardware, yes, sir, sure.
Mm-hmm.
If we are having
So,
a good pixel of image, but we are using a black and white printer, so we can't get the same quality of image.
correct,
So
correct,
we should
correct.
have that the printer quality also. Hardware
Exact.
should support the software.
Correct,
That's what my
correct.
question. So just please highlight the latest nozzle.
Yeah.
So what is which is available?
No, actually, you have T12 nozzles and you have T14 nozzles. Again, that will vary from one make to other make. The status is they may charge you more money, and then they may say that this is. But you may nowadays you may get even nozzles. Can it be outsourced, the open sourced, and you can get it reasonably good quality nozzles for the or even DIY kinds of printers for that matter. You can, but I don't have much in-depth knowledge, or so yeah. Maybe you can even ask some industry person. Maybe I don't know. Maybe you can contact Rakesh. I think Rakesh is also one of the speakers, right? In this, yeah, Rakesh may be the right person to answer your question. But I didn't experience much of these nozzles. By varying the nozzles, I didn't try much, but I tried with the status make machines with the Mojo and the other the dimension, which we have T12 and T14 nozzles, and we used to interchangeably use it for different materials like ABS or the other PC or nylon 12. But DIY kinds of printers, I'm not aware, and I never changed that nozzle actually. I'm not aware of that. Yeah. Yeah.
So, is there any questions? Hello, is there any questions from the participants? Sir, we have one question. Very nice section on, especially on standards. Please provide links for ASTM and ISO. I want links, website links, I think, for ASTM and
yeah, actually, some of majority of them is not freely downloadable, but they are charging. Actually, anyway, I will share. Yeah, I will share. I will share my PPT. No issue. You can. Yeah.
Okay, sir. If you type the same thing on the website, we'll link the PDF, or
yeah,
we have to give some money.
Sure. Yeah, I will share the PPT. Then you can. Yeah.
Okay, sure, sir. Yeah. So by this we can conclude. So we have wonderful session on the file format standards, qualification and certification of 3D printed parts. So from his lecture, we have studied the introduction of the 3D printing, that is the scope of the files, STL file formats, advantages of the STL files, problems and the challenges in and the files like gaps, future of 3D data, file formats, ASTM, ISO standards. And one of the highlighting point was splitting the model in the STL. If we are having the very complicated object, so we should first split the model into 2 halves or more number of parts, and we can modify that STL to get the better results. So that is a gaps. Gaps also one of the interesting topics. So how to control the gaps. If we have missing the small layer, that it will going to have the print on the whole. It will going to get beyond the extent of that layer. So he has also covered AMF, accuracy high, FDM, and various standards, the process parameters which affect the standards like product quality, reduce risk, and the cost will be reduced. And the assurance, that is bharosa, safety, production, quality, and monitoring and controlling. Again, one of the standard has to become in terms of the monitoring and controlling, as he said in the STM. And ISO and STM, ASTM agreement, that is ISO ASTM 2915 is the standard terminology for ASTM. And various standards under the process materials, test methods, design format, and under the material like titanium, nickel, vanadium, powder-based, and other materials. So it was a wonderful session, sir. We have learned a lot from this session again. And once again, thanks Dr. Y. Ravi Kumar, Associate Professor, Department of Mechanical Engineering, NIT Warangal, for giving a wonderful session, sir.
Thank you, Dr. Junaid. Thank you.
Thank you, sir.
Thank you. Okay, bye-bye.